Why, hello, AP Chemistry. Welcome back. We are going to keep talking about equilibrium and keep dealing with the math behind equilibrium. So, like we talked about yesterday, we're not really introducing any new concepts to these first couple math problems that we talk about. What we are going to do is just keep working with the idea of the concept of equilibrium and Q versus K in order to figure out the stoichiometry behind reactions that stop partway through. So we're just going to keep on moving down our line of practice problems. Here we are at a new practice problem that's going to introduce a couple variables to us. So what I want you to get to, I want you to try this, but I want you to get to where you have values for your equilibrium concentrations that aren't solved for yet. So get me values for equilibrium concentrations that involve an X. Get yourself there and then come back, check your work, and then we'll move on from there. Okay, so pause the video and try stuff. All right, gaseous hydrogen iodide is synthesized. So gaseous hydrogen iodide is going to be on this side of our equation from hydrogen gas and iodine vapor, H2, which is a gas, I2, which is a gas, at a temperature where the equilibrium constant, so K equals 100. Suppose HI at this, H2 at this, I2 at this are all mixed in a 5-liter flask. Calculate equilibrium pressures of all species. All right. So what we are dealing with, they've given us an equilibrium constant that is a Kp. And so they've given us partial pressures of all of these things in a 5-liter flask. So we actually don't need to calculate concentration because they already give us partial pressure. So I'm going to actually move this K so that I can fill in some of this information. So they give us K equals 100, and I can write my K expression, pressure of HI over pressure of H2 times pressure of I2, and let's balance this. So the top needs to be squared. Okay. That looks good. So now let's fill in information that they give us. HI is at 0.5 with lots of significant figures. Look at that. H2 is going to be at 0.01. And then I2 is going to be at 0.005. And these are our initial quantities. And I want equilibrium quantities. So I need C and E. So since I have amounts for all of these, before I go any farther, I need to calculate a Q to figure out which way this is going to shift. So let's calculate a Q. So my Q is at 5,000, which is bigger than K. So since my Q is bigger than K, my reaction needs to shift away from products. And I'm going to... Okay, so they're not all going to be the same amount of change because their coefficients aren't the same. So I can either do minus X for HI and then minus half an X for I2, or I can just double this one. think I'm going to go that route. So minus 2x plus x plus x. Okay. So now I have my equilibrium concentrations, 0.01 plus x, 0.005 plus x, and this is going to be 0.5 minus 2x. Okay, so if I plug this in now, so this is where we should be, this is where you should be. If you have gotten two equilibrium concentrations with a variable, this is where you should be. Are you here? Do you have questions? Did you get here? So now we're going to plug into K. So K is going to equal 0.5 minus 2x over 0.01 plus x times 0.005 plus x, and the top of this is going to be squared. Yikes. That's a beast. That's a beast of an equation. Okay, so here we go. We're going to do a little bit of review from Algebra 2, probably. Okay, so in order to solve this for x, we need to do some distribution, right? So let's distribute it all and see if we can get a nice little collection of x squares, x's, non-x's, and it all to equal 0. Something like that. There we go. Feels so good to practice those Algebra 2 skills, right? Okay, so we have ourselves at a quadratic equation here, right? So we have expanded, we have distributed, we have combined and simplified, and here we go. We have an equation that can't be solved unless we use a quadratic equation. So this is the point at which we pause and take a deep breath and try to remember the quadratic equation, right? So it's something like plus, it's like minus b, okay, x equals minus b plus or minus the square root, right? B squared minus 4ac all over 2a. I think that's it. It's something like that, right? Okay. Well, I'm going to tell you why I don't know the quadratic equation here in just a little bit. For two reasons. First of all, if you wanted to solve this equation, yeah, you actually legitimately do need to plug into the quadratic equation. However, we're going to work smarter, not harder, right? In this day and age, half of our success is learning to use the technology around us, right? There's a quadratic solver for you. And chances are, if you have a TI-81 or above, it's probably already on your calculator. So here's where, instead of plugging and chugging into the quadratic formula, You go figure out your calculator. Go do it. Look it up right now. Do you have a quadratic solving program on your calculator already? If you do, let's learn how to use it. If you don't, let's get one. There are quadratic formulas out there, quadratic programs that solve quadratic equations. You can program it on your calculator. It is totally legal to do that and use that on the test, right? And anytime you ever need a quadratic equation, when are you ever going to need one where you're not going to have your calculator sitting right next to you, right? The only thing I would say is don't go online and find an online quadratic equation solver because you're not allowed to use the internet for the test. Do it on your own calculator. You're allowed to use the calculator. You're allowed to program stuff into your calculator. So let's do it. Here's reason number 2 why I'm not super familiar with the quadratic equation. It's because there's a workaround. Not on this problem, but in the future, there's a workaround where we don't actually have to involve the quadratic equation most of the time. So I'm not going to teach you the workaround on this one because it is worth going and figuring that part of your technology out. Let's be smarter, not harder. It's going to pay off for you if you keep pursuing math and science. You're going to come across a quadratic formula. Let's know how to use your calculator. But in the future, real soon, I'm going to teach you the workaround. Okay, so we're going to plug it in. We're going to check out answers for X. All right, and what I got is X is equal to 0.0355. Okay, did you get that also? That's where you should end. Okay, now I have X. Woohoo! I'm done with the problem, right? Am I? Am I done with the problem? Okay, so again, this is where annotation pays off. What was the question asking? Was it asking us to figure out our change? No, it was not asking us to figure out our change. It was asking us to figure out equilibrium pressures. So X is not our answer. We have to go back and plug it in and figure out what our answer is. So let's do that, shall we? So this one's going to be 0.0455. This one's going to be 0.04. Let's see. Yeah, 0405. And this one is going to be 0.4645. And all of these are ATM. Now I have my answer. Okay, so again, same problem, slightly different context, slightly different logic getting to the answer, but we're going to approach it the same. We're going to approach it by writing out a reaction, writing out a K equation, writing out an ice chart. All right, here we go. Again, different problem. Let's try it again. I want you to get to the same place, get to that equilibrium positions with a variable, and then stop there. Actually, you can plug it into K. Plug it into K, stop there. Don't use the quadratic equation. I'm going to show you the workaround. Okay, here we are. This is our spot. So we've taken all our information, we've organized it into a reaction, a K equation, and an ice chart. Now we've gotten ourselves to the bottom, to these equilibrium concentrations. We've plugged it into K. And now we have a big, huge mess in front of us, and we need to solve for K. So here's the approach. We could push this forward, use the quadratic equation, multiply, expand, reorganize, plug it into the quadratic equation, solve out an answer for x, just like we did on the last one. However, before we do all that, let's make a consideration. So look again at our context, right? First of all, first piece of context I want to point out to you is that I never solved for a Q. I never plugged in Q, right? That's because I didn't have any reactant. So my Q automatically is 0. It's automatically too small, needs to proceed towards products in order to get bigger. So if there's something missing from your equation, you don't even have to calculate Q. You already know which direction it's going to, the reaction is going to proceed. Second of all, I want us to look at this equilibrium constant and tell me, is this a big equilibrium constant or a small equilibrium constant? It's a small equilibrium constant. So what does that mean? At equilibrium, when we're considering the ratio of products over reactants, there's not going to be very many products. The products are going to be very small when you compare them to the reactants. And therefore, we come out with a very small K. This K is very, very small, right? It's to the order of 10,000. So for every 10,000 reactant molecules, there's one product, one set of product molecules. This is not going to shift forward very far, right? So we can draw those conclusions just by looking at the magnitude of X. Sorry, the magnitude of K. So now that we know that this reaction is not going to proceed very far forward, now tell me about X. What do you know about X? Is X going to be very large or very small? Remember, X is our change, right? Basically. So if this is not going to proceed very far forward, there's going to be a very small change. X is going to be a very small number. Now, if X is small enough, it may not even affect other integers. So look at NaCl, for example. NaCl is 0.5 minus 2x. If x is on the order of the k, what would 0.5 minus something to the negative fifth, 10 to the negative fifth? 0.1, 2, 3, 4, 5. Okay, if we do this subtraction and then round off to significant figures, we get to keep 2. Okay, what are we going to end up with? We're going to end up with 0.5 again. So in terms of significant figures, if our change is small enough, it may not even affect other numbers that it is added to or that it is subtracted from. And if it's so small that it's not going to significantly affect numbers that it's added to or subtracted from, then we can ignore it, which would be nice. Now, it will affect, even if it's small, especially if it's small, it will affect things it's multiplied to, right? Because if you multiply a very small number, it's going to change your original number to the 10th or the 100th or the 1,000th order. It's going to change the order of the number you're talking to. That's a pretty significant change. But if it's just added or subtracted from something, then it's not necessarily going to have the same impact. So
Since we think this number is going to be so very small, because the K is small, the change is going to be small. It's going to be so small we can ignore it when it is added or subtracted to certain numbers. Chink! I'm going to ignore that. And now my equation becomes a whole lot simpler. 1.6 times 10 to the negative fifth equals 2x squared x over 0.5 squared. Okay, so now let's expand this out, multiply around. So this side becomes a 4x squared times x, 4x to the third equals okay, so this is going to be, I think, 4 times 10 to the negative 6. Now that's true unless my non-reliable calculator just rounded it off. Let me pull up a scientific calculator and do that again to make sure it didn't just round off. It didn't. Looks right. Okay. Divided by 4. Now, to get rid of the 4, I can just divide both sides by 4. But how do I get rid of the 3? Anybody remember? Algebra 2. You're going to raise it to the 1/3. So if you have a cubed root on your calculator, you can always just take the cubed root. But if you don't have a cubed root, just raise it to the 1/3. All right, and I got 0.01 equals x. So there you go. Now our change is 0.01. And I figured that out without using the quadratic formula. So this approximation can help you avoid the quadratic formula. Now, this can only be made under very specific circumstances. So this would be a good time to pause the video and think, when can this approximation be made? So we can ignore the change, we can ignore x if we anticipate the change is going to be very small. And we anticipate that a change is going to be very small when our k value is very small. When our k value is very small, then it tells us that our reaction is not going to shift towards products very much. At equilibrium, we're going to have a very small amount of products compared to the amount of reactants. Our reaction's not going to go forward very much, so we won't have very much of a change. That's the only time you can make this approximation. And your book will talk about a 5% rule. So once you get x down here, what you want to do is compare x back up here. And if the answer with the approximation is within 5%, then you can make this. Okay, so for example, if I take my assumed amount of NaCl versus if I were to plug this in to this equation, right? 0.5 minus 2 times 0.01 would be 0.48. So is 0.48 within 5% of my initial NaCl amount? I don't know. Let's find out. Yeah, it is. 0.48 is 96% of 0.5. So the difference between them is 4%. So if you're within a 5% difference, you can make this approximation. This is valid. And so my equilibrium concentrations, therefore, can use the x I found through making this assumption. 0.48 in this. Case. Let me erase this.
or not. All right, this would be 0.02 and this would be 0.01. There we go. Equilibrium concentrations. Chana! Same problem. We approached the problem the same way, still asking us for equilibrium concentrations. We wrote out the reaction, we wrote out an ice chart, we wrote out a K equation. We use those three to help us process them out, but it has a slightly different twist and turn in the middle of the problem. This is going to save you time. You can't always do this, but between your quadratic program that you figured out on your calculator and this approximation, it will get you through these practice problems a lot faster. Use this. All right, there's a practice problem we can do together. So here is a new concept. So we have practiced through using being functional within that K equation. Definitely do the practice problems in your book. Do not wait until the last day. You want to do these day by day by day so that you have a little processing time in between these problems. Okay, so we are moving on to a new concept, and this concept is called LeChatlier's principle. Now, if you speak French, you probably would not say this the same way that I say this, but I do not speak French, so we're going to call it LeChatlier's principle. And what this introduces us to are factors that can control the position of a chemical equilibrium. Again, we're not necessarily changing the K, but we're changing that ratio, which I guess would be changing the K. So it's going to control the positions of that chemical equilibrium. Instead of having a small amount of products, a large amount of reactants, can we actually push that so that we get more products and less reactants at equilibrium? Now, this was a lot of work was done around this principle around World War II by Fritz Haber. And Fritz Haber was trying to make as much ammonia as fast as possible. He was in the business of ammonia. He was trying to sell ammonia. So he did a lot of work trying to figure out how he could actually maximize the amount of ammonia that he made while minimizing the amount of reactants that he started with. Reactants were money. Reactants cost him money. Ammonia gave him money, right? He wanted lots of product, not a whole lot of reactants, so that he made a lot of money without wasting money spent on reactants. This is why the ammonia process that we look at over and over is often called the Haber process. So what he was doing was he was studying the effects of temperature and pressure on equilibrium. So that's what we're going to do now. You can use these concepts to figure out if there's a temperature change, how does that change equilibrium? If there's a pressure change, how does that change equilibrium? So that's what we're going to do now. All right, and then one last note before we kind of dive into this is, remember, we're talking about the ratio of products to reactants at equilibrium. We're not necessarily talking about how fast we get there. And so if you are in the business of synthesizing ammonia, for example, or some other compound, you're going to have to look at both factors. You're going to have to look at this equilibrium position as well as speed, because one does not tell you about the other. All right, let's go. First of all, concentration. What if we change initial concentrations? How will that affect where we are at equilibrium? So for example, let's say we have an equilibrium position of this. Okay, we have a specific amount of N2, a specific amount of H2, a specific amount of NH3, and then at equilibrium, 1 mole of N2 is suddenly injected. How will these equilibrium positions shift? Now, before we get going in this, Let's take a moment to pause and realize we've kind of been talking about this scenario all along. This is a scenario of starting with different initial concentrations, and this scenario will not change our ratio. This scenario will not change our K. It will change equilibrium positions, but K will be the same. Okay, so how will equilibrium shift? Well, let's calculate Q to find out. All right, so if we were at equilibrium, what would our initial K be? Let's just look at our reaction real fast. N2, H2, NH3, 2 of these. We need 3 of these, and then we're balanced. So our K equation here is NH3 to the second, N2, H2 to the third. All right, so now we can plug all of this in and figure out what our K is. All right, our K is 0.0596. All right, now if we were to add 1 mole of N2, our amount of N2 is no longer going to be 0.399, it's going to be 1.399. So let's just keep everything else the same and calculate a Q before any shifting occurs. All right, so I get a Q here with this information. Therefore, Q is going to be equal to 0.0170. So Q has gone down. Q is less than K. So in order for this equation, this reaction to shift and get back to K, what has to happen? The products have to get bigger, right? So this is going to shift right towards products. Shift right towards products. Okay, so this gets us to LeChatlier's principle. LeChatlier's principle basically says that if there's a stressor that's introduced to a system, so the stressor in this case would be an injection of N2. If there's a stressor, the system's going to shift to minimize that stressor. So if we inject a reactant, the system's going to shift away from reactants towards products to try to minimize the reactants. If we inject products, then the system's going to shift away from products and try and minimize the products. Same thing if we remove it. If we remove reactants, the system will shift to build those reactants back up. If we remove products, the system will shift to build those products back up. So whatever the stressor is, the system is going to shift in order to minimize that stressor. And that's exactly what we see here. We introduced a reactant, and then the system shifted towards products. It made more products. It reduced the amount of reactants we had, right? Again, worth noting, we did not change K. Our ratio remained constant, but our equilibrium positions changed in order to minimize the stressor. Okay, so welcome to LeChatlier's principle, and that is LeChatlier's principle in terms of changing concentrations. The general principle of LeChatlier's
principle will always be the same. The system is going to shift to minimize stressors, but the reasoning behind why it shifts will not always be the same. Okay, so we'll do this example together. Let's look at pressure. All right, so there's 3 different ways to change pressure. We can add or remove a reactant or product. We can add an inert gas. Inert means it's not reactive. So let's say we have only nitrogen inside my container. Well, if I have 4 molecules of nitrogen or 4 moles of nitrogen, and I add something inert, something that's not going to react with nitrogen, I add argon. Now I have more moles inside the same volume. I have increased pressure, right? Okay, so we can add a reactant, add a product, remove a reactant, remove a product. We can add an inert gas, or you can change pressure by changing the volume of the container, right? If we go back to our initial amount, our initial container that had 4 molecules of nitrogen in it, well, if we make that container smaller and we still have 4 molecules of nitrogen in it, the pressure is going to be higher, right? So we can mess with pressure a couple different ways. So first of all, let's look at these one by one. If we're adding or removing reactants or products, that's the same as what we were just looking at on the last slide. It's just like changing concentration. So we have already talked about the effect of changing concentration. It's going to be the same. If we add an inert gas is going to exert pressure equally on the reactants and the products. So adding an inert gas is not actually, since that inert gas isn't involved in the reaction, that inert gas isn't involved in the K equation, it's actually going to have no effect on equilibrium, right? Remember, we're going to figure out where our equilibrium pressures are by this reactant versus product ratio. Well, if our inert gas is nowhere to be seen in this ratio, it will actually have no effect on equilibrium. So adding an inert gas has no effect. Okay, let's take a look at number 3, changing the volume of the container. So in this case, changing the volume of the container, we're going to again see this effect of the LeChatlier's principle. It's going to shift away from the stressor. So if our reactants versus products have a different amount of moles of gas, the volume is actually related to the moles of the gas that are present. We know volume and moles are related because we've seen that relationship inside the gas laws, the ideal gas law, right? Volume is proportional to moles. If moles goes up, volume goes up. If moles go down, volume goes down, and vice versa, right? So it's really dependent on the moles of gas. Let's say I have 3 moles of reactant gas. Actually, we can look at the Haber process and not do something hypothetical. Let's do something real. Okay, doubled, tripled. All right, so look, on our reactant side here, how many moles of gas do we have? We have 4. On our product side here, how many moles of gas do we have? We have 2. Now, remember, the law of conservation of mass says that the mass in the beginning of a reaction is going to be the same as the mass in the end. The atoms are also conserved. The number of atoms in the beginning is equal to the number of atoms in the end. But is moles conserved? No, it's not. Is volume conserved? No, it's not. So this law of conservation of mass doesn't apply to every single unit, right? It applies to mass. It applies to atoms. It does not apply to molecules or moles or volume. It doesn't apply to a whole bunch of things. So our moles of gas is changing in this reaction. We're going to have 4 moles of gas in the beginning, 2 moles of gas in the end, right? So if let's say we have a system at equilibrium. We have established our ratio of reactants versus products, right? We have our established K at equilibrium. And then we shrink our container. Our system is going to shift to relieve the pressure. So it's going to shift. If we make the volume smaller, it's going to shift so that it makes the smaller amounts of molecules. If we make our reaction smaller, our system is going to shift towards products in order to have less volume inside that container. If we expand our container, our system will shift to fill that amount. So our system is going to shift in this direction so that we get more molecules of gas, more volume, more moles of gas, more volume of gas inside our container. So again, we're going to see this shift so that it minimizes whatever stressor we're putting it on. Okay, we have some practice on this page. We're going to go through this practice together. Very quickly, I want to introduce you to our last thing that can affect our equilibrium positions, and that's a change in temperature. Okay, so the other two changes have changed the equilibrium positions, but not the K. This one is going to mess with your K. So, but again, it's just the same concept, right? Our system is going to shift in order to minimize the stressor. So the thing is, we have to consider what our system is in terms of temperature. So in order to do that, we need to consider it in terms of either being endothermic or exothermic. So something that's exothermic is going to give off heat. The system is going to give off heat. If it's going to be exothermic, you can treat heat as if it's a product. Remember, something that's exothermic is going to be listed as a negative because the system is losing that heat, right? If it's endothermic, remember the system has to take in heat. So we're going to treat heat as if it's a reactant. And remember that if something is endothermic, if the system is absorbing heat, it's going to be listing that heat as a positive. So look at these two scenarios. If we have delta H, so the overall change in energy of our reaction is a negative 92 kilojoules, what we're going to do is we're going to put that heat as a product. If in the case of this one, we have a change in, that's exactly how it would be written. So notice the heat has been listed as a product. So now we can consider, now that we understand our system, now we can consider what would happen if we change the temperature. So let's say we increase temperature. Well, our system's going to shift away from the stressor, right? So if we increase temperature, our system's going to shift so that it decreases the temperature. It's going to shift away from our heat and absorb that heat so that the system's temperature goes down. If in the other case, we are going to decrease temperature, the system's going to shift to produce heat and minimize that stressor. So all of this comes down to the same idea. If a stressor is introduced, whether that's concentrations, pressures, or temperatures, our system is going to shift to minimize that stressor. And we will practice this together. And the more you practice this, the more it's going to make sense. Okay, jot down your questions. Let me know what those are. I will see you in class.